ਵਿਦਿਆਰਥੀਓ, ਕੋਆਰਡੀਨੇਸ਼ਨ ਕੰਪਾਊਂਡਸ ਦੇ ਸਟਰਕਚਰ ਅਤੇ ਬੌਂਡਿੰਗ ਦੇ ਨੇਚਰ ਨੂੰ ਐਕਸਪਲੇਨ ਕਰਨ ਲਈ ਕਈ ਸਾਇੰਟਿਸਟ ਨੇ ਕਈ ਥਿਊਰੀਜ਼ ਪ੍ਰਪੋਜ਼ ਕੀਤੀਆਂ। The first theory was called the Werner's theory of coordination compounds, which was proposed by Alfred Werner. His theory is based on the concept of primary valency, which is ionizable and is also referred to as oxidation state, and secondary valency, which is non-ionizable and is also called coordination number. But this theory could not explain formation of complexes by a few elements and also the directional nature, magnetic and optical properties of coordination compounds. Due to these limitations, Werner's coordination theory lost its relevance. ਅਤੇ ਤਿੰਨ ਮੁੱਖ theories valence bond theory, that is VBT, crystal field theory, that is CFT, ਅਤੇ ligand field theory, that is LFT propose ਕੀਤੀਆਂ ਗਈਆਂ। ਅੱਜ ਅਸੀਂ ਵੈਲੈਂਸ ਬੌਂਡ ਥਿਊਰੀ ਬਾਰੇ ਵਿਸਥਾਰ ਵਿੱਚ ਪੜਾਂਗੇ ਅਤੇ ਨਾਲ ਹੀ ਬੌਂਡਿੰਗ ਇਨ ਕੋਆਰਡੀਨੇਸ਼ਨ ਕੰਪਾਊਂਡਸ ਅਤੇ ਐਪਲੀਕੇਸ਼ਨਸ ਆਫ ਕੋਆਰਡੀਨੇਸ਼ਨ ਕੰਪਾਊਂਡਸ ਬਾਰੇ ਵੀ ਜਾਣਾਂਗੇ। Let us first take up valence bond theory. Do you know that this theory was extended to the coordination compounds by Pauling in 1931? It is based on the concept of hybridization. We will now discuss the main postulates of this theory. In this approach, the basic assumption is that when the ligands approach the metal atom or iron metal, ligand coordinate bond arises by orbital overlap, resulting in the donation of pairs of electrons by ligands to the metal atom or ion. In order to accommodate these pairs of electrons, the central metal atom or ion must provide requisite number of vacant orbitals of equivalent energy equal to its coordination number. These orbitals of equivalent energy are obtained by hybridization of the suitable number of the atomic orbitals of the metal atom or ion. In case of d orbitals, if inner d orbitals, that is n minus 1 d orbitals, are used in hybridization, the complex is called inner orbital or low spin complex. And if outer n d orbitals are used in hybridization, the complex is called outer orbital or high spin complex. A substance which does not contain any unpaired electron and is not attracted by magnet is called diamagnetic. On the other hand, a substance which contains one or more unpaired electrons in the d orbitals is attracted by a magnetic field is called paramagnetic. Paramagnetism can be calculated by the expression
mu s is equal to square root of n into n plus 2.
Bohr magneton.
Here mu is magnetic moment. S is spin only value and n is number of unpaired electrons.
On the basis of value of magnetic moment, we can predict the number of unpaired electrons present in the complex. If we know the number of unpaired electrons in the metal complex, then it is possible to predict the hybridization and hence geometry of the complex species. There are two types of ligands, namely strong field and weak field ligands. Strong field ligand is capable of forcing the electrons of the metal atom or ion to pair up against Hund's rule of maximum multiplicity if required. Pairing is done only to the extent which is required to cause the hybridization possible for that coordination number, whereas a weak field ligand cannot. Examples of strong field ligands are carbonyl carbon, monoxide, ammonia, cyanide ion, pyridine, etc. Let us now discuss bonding in coordination compounds. Let us have a look at few examples. Let us first take up example of octahedral complexes with coordination number is equal to 6.
Let us have a look at the formation of hexaamine cobalt 3 ion. Cobalt atom has atomic number Z is equal to 27 and has outer electronic configuration 3d7 4s2. In this complex, cobalt ion is in +3 oxidation state and has the electronic configuration of 3d6 as shown on screen. Experimentally, this complex has been found to be diamagnetic. The reason behind this is that the two electrons in the 3d orbitals are paired up, leaving two 3d orbitals empty as shown on screen. Those 6 vacant orbitals, that is, two 3d orbitals, one 4s and three 4p orbitals, hybridize to form d2sp3 hybrid orbitals. 6 pairs of electrons, one from each NH3 molecules, are donated to these vacant hybrid orbitals. Thus, the complex has octahedral geometry and is diamagnetic. Since the inner d orbitals are used in hybridization, the complex is called an inner orbital or low spin complex.
Let us take another example.
Let us have a look at hexafluorocobaltate 3 ion. In this case, cobalt ion is in +3 oxidation state and has outer electronic configuration 3d6. This complex has been found to be paramagnetic due to the presence of 4 unpaired electrons. To account for this, the electrons in the 3d orbitals are not disturbed and its 4d orbitals are used for hybridization, as shown on the screen. The 6 orbitals, that is 1 4s, 3 4p and 2 4d orbitals are hybridized, forming 6 sp3d2 hybrid orbitals. 6 pairs of electrons, one each from fluoride ion, are donated to the vacant hybrid orbitals, forming cobalt ligand coordinate bonds. Thus, the complex has octahedral geometry and is paramagnetic. As 4d orbitals are used in hybridization, the complex is called an outer orbital or high spin complex.
Now let us take examples of complexes with coordination number 4. The geometry will be tetrahedral or square planar depending upon whether sp3 or dsp2 hybridization is involved. Let us first have a look at the tetrahedral complex.
Tetracarbonyl nickel 0 complex. Here nickel atom has atomic number Z is equal to 28 and has outer electronic configuration 3d8-4s2. For complexes with coordination number 4, the central atom involves either sp3 or dsp2 type of hybridization, for each of which the 4s orbital must be empty. The electrons of 4s orbitals are forced into 3d orbitals to pair up, leaving empty 4s orbitals, as shown on screen. Thus, 4 vacant orbitals, that is, 1 4s and 3 4p orbitals, hybridize to form sp3 hybrid orbitals. 4 pairs of electrons, one from each carbonyl ligand, are donated to these vacant hybrid orbitals. Therefore, the complex is diamagnetic. This results in sp3 hybridization, and the complex has a tetrahedral structure.
Let us take another example.
Formation of tetraamine zinc 2 ion. Zinc atom has atomic number Z is equal to 30 and has outer electronic configuration 3d10 4s2. In this complex, zinc ion is formed by losing two 4s electrons and has the electronic configuration of 3d10, as shown on screen. The 3d orbitals are fully occupied. Therefore, they cannot participate in hybridization. 4 sp3 orbitals can be formed by mixing 1 4s and 3 4p orbitals, as shown on the screen. These 4 sp3 hybrid orbitals accommodate 4 pairs of electrons from 4 NH3 molecules. The resulting complex is tetrahedral and will be diamagnetic as there are no unpaired electrons.
Let us now learn about the square planar complexes.
Let us have a look at the formation of tetracyanonickelate 2 ion. The nickel atom has atomic number Z is equal to 28 and has outer electronic configuration 3d8 4s2. In this complex, nickel ion is in +2 oxidation state and is formed by losing two 4s electrons and has the electronic configuration of 3d8, as shown on screen. We know from experiments that the complex is diamagnetic. The reason behind this is that the two unpaired electrons in the 3d orbitals are paired up, leaving one 3d orbital empty, as shown on screen. These 4 vacant orbitals, that is, one 3d orbital, one 4s and two 4p orbitals, hybridize to form dsp2 hybrid orbitals. 4 pairs of electrons, one from each cyanide ion, are donated to these vacant hybrid orbitals. Thus, the complex has square planar geometry and is diamagnetic.
Let us take another example.
Let us discuss the formation of tetraamine copper 2 ion. Copper atom has atomic number Z is equal to 29 and has outer electronic configuration 3d10 4s1. In this complex, copper ion is in +2 oxidation state and has the electronic configuration of 3d9, as shown on screen. This complex has been found to be paramagnetic. To explain this, it was proposed that one unpaired electron in d subshell is promoted to one of the orbitals of 4p subshell. The resulting vacant 3p along with 1 4s and 2 4p orbitals hybridize to give 4 equivalent dsp2 hybridized orbitals. 4 pairs of electrons, one each from ammonia molecule, occupy the 4 vacant hybrid orbitals as shown on the screen, thus forming a square planar complex.
Let us now discuss drawbacks of valence bond theory. Although valence bond theory successfully explains the geometry of the shapes and magnetic behavior of the coordination compounds, but has a number of shortcomings. Let us try to list a few of them. It involves a number of assumptions. It does not give quantitative interpretation of magnetic data. It fails to explain the absorption spectra of coordination compounds. It does not give an exact explanation of thermodynamic or kinetic stabilities of coordination compounds. It does not make exact predictions regarding the tetrahedral and square planar structures of coordination compounds. It does not distinguish between weak and strong ligands. It cannot explain why some complexes of a metal ion in a particular oxidation state are low spin, that is, inner orbital complexes, while some other complexes of the same metal ion in the same oxidation state are high spin, that is, outer orbital complexes. For example, CuNH3 3 positive is a low spin diamagnetic, that is, inner orbital complex involving D2 sp3 hybridization, while CuF6 3 negative is a high spin paramagnetic, that is, outer orbital complex involving sp3 D2 hybridization. The magnetic behavior predicted by valence bond theory is sometimes misleading. For example,
the square planar complex of nickel 2 should be diamagnetic. This is because for dsp2 hybridization, the two unpaired electrons of Ni2 plus pair up as shown on the screen. Thus, we may wrongly assume that all the square planar complexes of nickel 2 should be diamagnetic, but it is actually not so. Some square planar complexes of nickel 2 are known, which are paramagnetic. In their cases, we assume that one of the paired 3d electron is excited to 4p orbital, so that two unpaired electrons are present as shown on the screen.
valence bond theory cannot explain as to why excitation occurs in one square planar complex but not in the other. Similarly, in the case of this CuNH3 2 positive complex, let us move on to important applications of coordination compounds. Let us first have a look at its applications in the field of analytical chemistry. In qualitative analysis, in salt analysis, the presence of a number of basic radicals is confirmed by converting them into suitable complexes which have definite colors. Let us have a look at the reaction shown on the screen.
Here, when dimethyl glyoxime is added to nickel salt solution in presence of ammonium hydroxide, a brilliant red precipitate is formed due to the formation of a complex of nickel ions with dimethyl glyoxime confirming the presence of nickel ions. Next, in quantitative analysis, that is, in estimations. Gravimetric analysis. The amount of metal present in a given sample can be estimated by converting a known amount of the sample into an insoluble complex, which can be filtered, dried, and weighed. For example, the amount of nickel present in a salt is estimated by precipitating it as nickel dimethyl glyoxime complex.
In metallurgy, that is, in extraction of metals, the noble metals like silver and gold are extracted from their ores through the formation of their respective cyanide complexes.
For example, silver is extracted from its ore by first dissolving the ore in NaCN solution and then precipitating out silver by adding the more electropositive metal zinc. In purification of metals, some metals are purified by formation of their metal carbonyls followed by their decomposition. Example, impure nickel is converted into nickel tetracarbonyl, which on decomposition gives pure nickel. In biological systems, a number of biologically important compounds are the coordination compounds that are the metal complexes. Their use is mainly due to the fact that they are soluble complexes and thus make the metal available to the biological systems which may not be otherwise easily available. A few examples in biological systems are chlorophyll, the green plant pigment that acts as a photosensitizer in the photosynthesis in plants, is a coordination compound of magnesium. Hemoglobin, a red pigment of blood which acts as an oxygen carrier, is a coordination compound of iron. Vitamin B12, which is chemically cyanocobalamin, is the anti-pernicious anemia factor, is a coordination compound of cobalt. In catalysis, coordination compounds are used as catalysts for many industrial processes. Examples include rhodium complex, a Wilkinson catalyst, is used for the hydrogenation of alkenes. Electroplating. Articles can be electroplated with silver and gold much more smoothly and evenly from solutions of AgCN2 negative and AuCN2 negative, the shown complexes, than from a solution of simple metal ions. Photography. In black and white photography, the developed film is fixed by washing with hyposolution, which dissolves the undecomposed AgBr to form this AgS2O3 2,3 negative complex ion. In medicines, there is a growing interest in the use of chelate therapy in medicinal chemistry. For example, the chelate complex of calcium and EDTA is used in the treatment of lead poisoning. Inside the body, calcium in the complex is replaced by lead. The more soluble lead, EDTA complex, is eliminated in urine. Removal of excess of copper and iron present in plant or animal systems by complex formation by chelating ligands d-penicilliamine and desferrioxime B. In industry, for example, sodium salt of EDTA is used in mercerizing of cotton and prevents grayness of rayon yarn due to precipitation of lead sulfide. In textile dyeing, sodium salt of nitrilotriacetic or NTA controls the interfering heavy metal ions which affects the color shade and fastness. Complexing agents are used in the refining of vegetable oils and used lubricating oils. Chelating agents like EDTA and NTA are widely used as descaling agents in sugar industry and in dairy processing. Chelating agents are also used in rubber industry as antioxidants, that is, to inhibit oxidation due to the presence of heavy metal ions and thus increase life of rubber. Complexing agents are used in paper and pulp industry, in leather industry, in polymer industry. These are used as corrosion inhibitors in foundry for estimation of aluminium in steel and in laboratory for cleaning of sintered glass crucibles. Chelating agents are also used in plastic emulsion paints. Traces of metal impurities in the form of ions, if present in these emulsions, can affect the stability of these emulsions. This can be prevented by using complexing agents like EDTA, which inactivate these metal ions.
Children, let us now try to solve a problem. The spin-only magnetic movement of tetrabromide manganate 2 ion, that is MnBr4 2 negative, is 5.9 Bohr magneton. Predict the geometry of the complex ion. Now let us try to find out the solution for this problem. The coordination number of Mn2 positive ion in the complex ion is 4. Therefore, it will be either tetrahedral involving sp3 hybridization or square planar involving dsp2 hybridization.
As calculated from the equation shown on the screen, the complex has 5 unpaired electrons. Since it has 5 unpaired electrons, this means that the 3d orbitals are not disturbed, and thus sp3 hybridization occurs, resulting tetrahedral structure of the complex as shown on screen.
My next question is, look at both the structures on the screen. Between the two, which species has square planar geometry and why? Explain with the help of VBT.
Nickel atom has atomic number Z is equal to 28 and has outer electronic configuration 3d8-4s2. In this complex, nickel ion is in +2 oxidation state and is formed by losing 2 4s electrons and has the electronic configuration of 3d8 as shown on screen.
Due to smaller size of cation Ni2 positive and larger size of anion Cl negative, the steric hindrance comes into play. Ni2 positive goes under sp3 hybridization involving 4s, 4p orbitals, and thus the geometry of complex ion is tetrahedral. Let us move to second complex ion.
Platinum atom has atomic number Z is equal to 78 and has outer electronic configuration 5d8 6s2. In this complex, platinum ion is in +2 oxidation state and is formed by losing two 4s electrons and has the electronic configuration of 5d8 as shown on screen.
Cation Pt2 positive is larger in size than anion Cl negative. Hence, the steric hindrance does not come into play. Due to this, 5d8 electrons of Pt2 positive under the approaching Cl negative ions get forced pair. As a result, Pt2 positive goes under dsp2 hybridization involving one of the 5d 6s, two of 6p orbitals, and thus the geometry of complex ion is square planar. मैनू उम्मीद है कि तुहानू अज दा एपिसोड काफ़ी इंटरेस्टिंग लग्या होएगा। ध्यान देने लई धन्यवाद। अगली क्लास विच एक होर नवे विषय नाल फिर मिलांगे। तद तक लई गुड बाय।